The Moon. As close as we can see with our own eyes, just 384,000 kilometers away, the place where 12 astronauts walked, our greatest achievement in space. But it is also our greatest delusion, because our closest neighbour may in fact be our most unreachable fortress. The radiation there is hundreds of times greater than on Earth. This is why, to protect a single room, you need to cover it with a full 500-ton shield. But getting that shield there is impossible, because only 2% of the rocket you launch actually reaches the target. And here is the greatest paradox. When you land there, you will feel 84% lighter, but that very lightness will melt your bones, never to return. But the truly disturbing question is this: what is the probability that those who go there will never be able to return to Earth? If these impossibilities excite you, hit like and subscribe right now, because this journey is far darker than you imagine. We are beginning. For years we looked at the Moon and thought how close it is. Just 384,000 kilometers away, a neighbour visible to the naked eye. 12 humans even walked on its surface. And so we assumed that building a permanent base was the next logical step. But in this assumption we overlooked a fundamental error. Because the greatest obstacle was not distance. The greatest obstacle was not even engineering. The real problem was a ruthless mathematics that most people fail to notice. And so everything begins with the rocket equation. Not the vacuum, not the dust, not the radiation. Those will come later. The first barrier is math. And that math is not linear. This is the part that most people miss. Because on Earth, things work with a simple logic. To carry more material, you send more trucks. The relationship is almost 1-to-1. Double the cargo, double the fleet. This scaling feels manageable, like a construction budget. But space does not work like this. Space is a war fought with exponents. At the heart of rocketry is a relationship that connects three things: the speed you need to reach, the mass of the rocket when it is full of fuel, and its mass when that fuel is gone. You don't need the formula, you just need to understand its shape. Because, as the required speed increases, the ratio of the full mass to the empty mass does not increase by the same amount. It rises disproportionately, at a steep angle. Every additional kilometer per second of speed you need costs more than the one before it. In practice, this has a terrifying meaning. Reaching low Earth orbit is the first step into space. This step requires a velocity change of about 9.4 kilometers per second. That's about 33,840 kilometers per hour. But to land on the Moon's surface from orbit and get back to orbit again requires roughly another 6 kilometers per second. And every single bit of that speed is paid for with fuel. Consider a typical large chemical rocket. About 85 to 90% of its mass at launch is just fuel. A 100-ton rocket sitting on the launch pad is perhaps only 10 to 15 tons of structure, engines, and the payload it carries. And the actual payload is only a small fraction of that 15 tons. But the truly shocking fact comes now. When you stack the stages required to go from Earth orbit to the Moon, the portion of the initial launch mass that becomes usable equipment on the surface drops dramatically. The working figure is about 2 to 3%. This is not a modest loss. It is not a rounding error. Just 2 to 3%. Here is what that number means in concrete terms. Imagine a 50-ton pressurized module on the lunar surface. This is equivalent to the mass of a large road truck, a single room with equipment inside. At 2% efficiency, that single room means an initial tower on the launch pad of about 2,500 tons, a full 2.5 million kilograms. And most of that immense mass was built, launched, and burned just to set one room down on the dust. It is a fuel iceberg. The module is that tiny peak above the water. Everything beneath it, the fuel, the tanks, the stages, has burned away along the flight path. And so, that 50-ton module is not a base. It is just a single room. A real base requires so much more. Radiation shields, rover vehicles, a power system capable of operating through the 14-day lunar night, food, water, air, water purification systems, waste processors, medical equipment, communication devices, computers, tools, pumps, valves, and circuit boards. And since there is no spare parts shop nearby, 2 or 3 backups of every critical system, plus spare parts. Because a small rover weighs hundreds of kilograms, a serious power system weighs tons. An extra 10 tons of equipment landed on the moon can mean hundreds of tons of extra fuel and hardware launched from Earth. And this is where things get even stranger. The structure holding all this equipment must itself hold more equipment than initially planned. Stronger floors, heavier walls, more supports. But a stronger structure means more weight, more mass means more fuel, and more fuel requires larger tanks and bigger rockets to push that fuel. It's a vicious cycle. And this cycle does not close gently. It turns into a self-feeding monster. And so, we must consider what distance truly means. The moon is about 384,000 kilometers away. Compared to the distances to Mars or beyond, this seems close. It is close in kilometers, but a rocket does not measure distance in kilometers. It measures it in energy. Because going to the moon means escaping Earth's deep gravity well, completing an interplanetary transfer, and performing a powered descent against the moon's gravity. The kilometers are almost meaningless. It is all energy. Even if you reach low Earth orbit at an optimistic cost of $1,000 per kilogram, that is only the first step. Getting from orbit to the surface requires additional stages, and most of the mass of those stages is again fuel. And so the effective cost of every single kilogram landed on the moon can reach tens of thousands of dollars. 1 kilogram is roughly a litre of water. The single litre of water delivered to the surface could cost more than most people earn in a month. A 100 kilogram rack of electronics or a 90 kilogram human carries a price tag in the millions of dollars. The imagined base is not made of walls and air. It is first built from pillars of money, converted into fuel. This is the first filter. Not the engineering challenge of building a habitat, not the medical challenge of protecting a crew. The first question is whether a civilization can afford the money to lift and land all that hardware, all the spares, all the backup stages, at a pace fast enough to keep a base alive. Because, when you combine the rocket equation with the combined mass of everything a human outpost requires, the answer moves from hard to the border of almost impossible for a normal economy. But the rocket equation is only the beginning of the problem. Because, once you land, the environment waiting on the surface has its own plans for everything you manage to bring. Because, let's assume we can somehow pay for the launch. Let's imagine the rocket equation is somehow solved and the hardware has landed. A crew steps onto the lunar surface, but the first thing that greets them is not the dust, or the darkness, or the silence, though all of those are waiting. The first thing that greets them is invisible. It is the sky itself. Because, on Earth, you are surrounded by 2 shields you never think about. The first is the atmosphere, a column of air roughly 1 bar thick above your head, a column of gas that absorbs and scatters a huge amount of solar and cosmic radiation before it reaches you. And so, you are protected. The second is Earth's global magnetic field. This field deflects charged particles from the sun and from deep space, bending them away like a river parting around a stone. But, on the moon, there is neither. The lunar surface is under a near-perfect vacuum. There is no thick blanket of air. There is no strong global magnetic field. High-energy particles from the sun and from sources far beyond the solar system slam into the surface almost unimpeded. This is the baseline. Not a special event, not a storm. This is the normal environment, every single day. Measurements from lunar orbit and the surface put the typical daily radiation dose under normal conditions at around a few hundred microsieverts per day. A person on Earth receives only a few microsieverts per day from the natural background, a few millisieverts in a year. But the rate on the Moon is several times higher, persistently, every day. This is the new normal. A year on the unprotected surface would consume a large fraction of a professional radiation worker's allowed annual limit. And that's assuming there are no storms. But storms happen. The Sun periodically erupts with solar particle events. During large flares and coronal mass ejections, enormous numbers of high-energy protons are thrown outward. Near Earth, the magnetic field and atmosphere absorb most of this. But on the Moon, the particles arrive directly, and so a strong event can deliver over a sievert of radiation in just a few hours, even behind a thin shield. A sievert is 1,000 millisieverts. At this level, the long-term cancer risk is clearly elevated. A rapid dose of several sieverts leads to acute radiation sickness, nausea, vomiting, damage to blood cells and bone marrow, and at high enough doses, it can be fatal without immediate treatment. That clean white dome design is not a viable design. This is where engineering forces its way in. To protect against both the constant baseline and the sudden spikes of a storm, the habitat needs serious shielding. Not a thin aluminium shell, not insulation. Meters of material. Lunar regolith piled thick overhead. Dense regolith brick walls, or tanks of water placed around the living spaces. Because water is actually an effective radiation shield. The hydrogen atoms in water are good at absorbing and scattering high-energy particles. But water is heavy. Everything is heavy, and heavy things must pass through the rocket bottleneck described in the first problem. Some planners suggest sending the shield directly from Earth. Let's consider what that actually means. To reduce high-energy galactic cosmic rays to acceptable levels, a significant amount of mass is needed per square meter of roof and wall. Estimates range from roughly 5 to 10 tons per square meter. Imagine a modest habitat with about 100 square meters of exposed surface area. This is equivalent to the floor space of a modest house. At 5 tons per square meter, this habitat needs 500 tons of shielding. At 10 tons per square meter, 1,000 tons. That figure is just the shielding itself. Before the structure, the life support, the power systems, the crew. 500 to 1,000 tons of shielding for just one small habitat. With the launch math from the first problem, that number becomes something no existing economy could afford without an extraordinary national commitment. And so, importing the shield from Earth is not a backup plan. It is not a fallback. It is essentially impossible as a solution for routine operations. And so, the answer is to use what is already on the Moon. The regolith is free. The surface is covered in meters of it, a fine-grained, loose material crushed by billions of years of micrometeoroid impacts. The right instinct is to dig it up, pile it on top, use it as a natural radiation blanket. This is a correct instinct. But it does not solve the problem. It displaces the problem. Because moving regolith requires excavators, loaders, bulldozers, machines that dig trenches and fill heavy bags, or 3D printers that turn regolith into bricks. And all of them must survive for years in the lunar environment. Temperature swings of over 250 degrees between lunar day and night, reaching over 100 degrees Celsius in the sunlight, or plunging to around minus 170 degrees Celsius in the shade. Sharp abrasive dust gets into every seal and bearing. The vacuum changes how lubricants behave. And every excavator, every spare motor, every hydraulic seal is a mass that had to be lifted from Earth, put on a lunar transfer trajectory, and soft landed. Because the rocket equation does not go away just because you decide to use local materials. It re-enters through a side door, and then there is the part the numbers cannot solve. Because the data does not exist. We have never tested human biology for years, under the specific combination of deep space radiation and low gravity. All long-duration spaceflights so far have been on the International Space Station, still within Earth's protective magnetic field and in microgravity, not 1/6 gravity. A lunar base crew would face a different radiation environment and a different gravity environment simultaneously, for years. And there is no historical data on what that combination does to cardiovascular health, bone marrow, the nervous system, or long-term cancer risk. A lunar base would be that data set. The people living in it would generate the evidence themselves, while relying on their own health to keep the base operational. They would be both the subjects and the repair crew at the same time. If the results turn out to be worse than predicted, there is no clean undo button, because bringing a full resident population back to Earth is enormously expensive, and some of those residents, after years in 1/6 gravity, may never be able to withstand full Earth gravity again. Biology could become irreversible in ways we do not yet know. Perhaps careful shielding and protective medicine keep the risk at manageable levels, or perhaps the combination of radiation and low gravity interacts in ways current models underestimate, producing higher rates of cancer, accelerated cardiovascular disease, damage to the nervous system, and so, both outcomes are genuinely possible. Neither has been ruled out. Radiation alone transforms the Moon from a place you visit briefly into a place that constantly consumes a health budget that cannot be easily replenished. And it's wrapped in an infrastructure so heavy that it makes the rocket equation even worse all over again. Or because the shielding problem and the biology problem together are just the second challenge. The surface itself still has more in store, and now comes the real shock. Because, put biology aside for a moment, the slow accumulation of invisible damage to the body is one kind of threat. The surface itself presents another kind entirely, and it is visible, measurable, and extreme in ways most Earth engineering is never asked to deal with. Watch the Moon's day turn to night. This is not a familiar 24-hour cycle with a brief cool night and a warm afternoon. The Moon completes one full rotation relative to the Sun in about 29.5 Earth days. That means roughly 14 days of continuous sunlight, followed by roughly 14 days of complete darkness. And this cycle continues, month after month, year after year. And so, in that direct sunlight, the surface temperature climbs to about positive 120 degrees Celsius, or 250 Fahrenheit. But when the sun dips below the horizon and the long night begins, the surface temperature plummets to minus 170 degrees Celsius, or minus 274 Fahrenheit. The total swing between these two extremes is close to 300 degrees Celsius, not over seasons, like the Earth cycles between summer and winter, but within a single month, over and over again. Because metals expand when hot and contract when cold, seals stiffen in the cold and soften in the heat. Solder joints flex with every cycle. Wires, hinges, connectors, and pipe fittings are pulled in one direction for 2 weeks, then the other direction for 2 weeks. On Earth, most machines see swings of a few tens of degrees a day. But lunar hardware is dragged across a range of almost 300 degrees repeatedly, and so small stresses accumulate. Tiny cracks grow, seals lose their grip. The structure not only has to survive the temperature, it is running a slow-motion fatigue test on itself, continuously, for years. Inside, the crew needs something close to normal room temperature, about 20 to 25 degrees Celsius. The habitat walls must maintain this stable interior against whichever extreme the surface is offering at that moment. Roasting outside during the long day, freezing during the long night. And so, thermal control cannot stop. It cannot fall behind. Because to fall behind during the day means the interior overheats. To fail during the night means pipes freeze and the air becomes dangerously cold. And all of this happens while the surrounding structure is contracting and expanding with the same cycle. Solar power seems like an obvious answer on the Moon. No clouds, no air, no atmosphere to scatter the light. The panels sit in clean, hard sunlight and convert efficiently for about 14 days. Solar works well. But Then the sun sets and the output drops to essentially zero. To keep life support running through the lunar night of more than 350 hours, the base needs stored energy. Life support alone requires continuous power for air circulation, carbon dioxide removal, oxygen generation, water circulation, and heating. Add computers, lighting, communications, and the base is always drawing somewhere between tens and hundreds of kilowatts. Multiply that continuous draw by roughly 14 days, and you arrive at megawatt hours of stored energy. But now add the heat rejection problem. Even once power is solved, all of that power eventually becomes waste heat inside the habitat. On Earth, you dump waste heat into the air around you. The atmosphere carries it away. On the Moon, there is almost no air. Convection, the process of heat moving through a circulating fluid or gas, essentially does not work. Heat can only leave through direct solid contact with something else, or through radiation. Radiation means infrared light, an invisible glow of energy shining out into space. And so, the base needs radiators. Large panels oriented to face cold space. Panels that glow in the infrared, slowly shedding heat. This is the only viable cooling mechanism available. But the same regolith that shields the habitat from radiation turns the cooling problem into a conflict. The buried bunker that solves radiation also wraps the habitat in one of the best thermal insulators on the Moon. Because regolith does not conduct heat well, which helps slow the brutal swings from the outside. But that becomes a serious hindrance when you need to move heat from inside the habitat to a cooler radiator. You find yourself with a habitat wrapped in a thermal blanket, trying to pump heat through that blanket to emitter panels that need to see clear space without being shadowed by your own structure. And the thermal control system that does all this is not a single device. It is pumps, pipes, valves, heat exchangers, and radiators. They work together across a range from the warm interior to the deep cold outside. And a pump, stopped by a partially frozen lubricant, can crash the entire cooling loop. A cracked pipe can bleed out coolant and end temperature control with little warning. And so, during the long day, it fights the heat from the scorching outside, while also dumping the heat generated inside. During the long night, it prevents freezing while still moving waste heat out to space. It has to do both, for years, without failure. And outside that controlled bubble, the exposure is even worse. Because any piece of equipment left idle during the long night, a parked rover, a robotic arm waiting between tasks, a crane, can soak to below -150 degrees Celsius for 2 full weeks. Many lubricants freeze solid or become gummy. Different metals shrink by different amounts, pulling at connections from multiple directions. And so, imagine a car parked in a deep freezer for 2 weeks. Then it is expected to start and drive at full performance. And this is repeated hundreds of times over several years. Bearings wear out faster, coatings crack, wires stiffen and eventually break. Most space hardware in use today is not tested for hundreds of these extreme cycles, while also doing heavy industrial work. Designing machines to last for decades in these conditions pushes materials and engineering far beyond what Earth industry normally demands. And every single failure in this environment means a spare part that was launched at enormous cost, and a human in a pressurized suit, working in those same thermal extremes to make the repair. Because the biology problem and the radiation problem together were the second challenge, temperature is the third. And the list does not end here. Stay outside for another moment. Look at what surrounds the equipment. The walls, the connections, the sealed doors. Not cold air, not a thin atmosphere, not even a trace of pressure. Nothing. An absolute void stretching uninterrupted in every direction. And that nothing is the fourth challenge. Because inside a lunar habitat, the air needs to be at a pressure of about 50 to 100 kilopascals. That's about half to full sea level pressure on Earth, roughly 7 to 15 pounds per square inch. Outside, the pressure is so close to zero, it might as well not exist. This vacuum does not let up. It does not relax at night or during quieter operational periods. It is there every second the base is occupied, and it pushes outward on every surface the habitat has. Consider what that constant load does to a structure. Every square metre of wall, ceiling, floor, window, airlock, hatch and joint is part of a single pressurized vessel trying to inflate outward, like a balloon held inside a rigid shell. On Earth, a cracked wall sags and leaks water. You call someone. But, on the Moon, a through-and-through crack vents breathable air directly into the void. The habitat begins to lose pressure, and the crew has minutes at best to reach a sealed volume, close the hatches and stop the loss. Not hours, minutes. That single consequence reshapes every decision about how the structure is built and maintained. Every weld must be sound. Every bolt must stay tight through decades of thermal cycling. Every seal must keep its flexibility without developing microcracks or losing its seal. There is no threshold for good enough. The structure must behave like a spacecraft or a submarine, a vessel that cannot afford a gradual failure. But this is not a spacecraft that flies for a week and returns. It is a place where people live for years, constantly entering and exiting, modifying, expanding, and repairing it, while the pressure load never eases. But the reality was different. The most dangerous failure mode is not the dramatic one. A rapid depressurization from a major breach is terrifying, and it is important to plan for it. But the quieter enemy is harder to find and stop, because air molecules are small and they are in constant motion. Every path through the shell, no matter how tiny, leaks gas. A microscopic pinhole, an imperfect seal line along a hatch frame, a hairline scratch in a gasket seat that allows molecules to pass through single file. These leaks are invisible, they make no sound, and they are relentless. A few grams of air per second seems almost negligible, but a habitat holds a few tons of breathable air. A constant, undetected leak at that rate can deplete the reserves in hours to days without triggering obvious alarms. And so, the base needs pressure sensors in every section, constantly comparing their readings, flagging drops that might be a real loss against drops that might be instrument error. It needs automated isolation valves between modules, so a compromised section can be sealed off before it fills the entire habitat with emergency conditions. And redundancy is a double-edged sword. A false alarm that seals off half the base at the wrong time is also dangerous. But now come to the real question. What about the people who have to find a leak that could be anywhere on hundreds of square meters of shell and repair it from the inside? Because leaks don't always appear right away. A flaw can sit dormant for the first 50 thermal cycles and open up on the 100th. A nearby micrometeoroid impact can flex the wall just enough to open a seal that has been on the edge for months. Some flaws only appear under full working pressure, invisible at lower loads. On Earth, you spray soapy water on a suspect joint and watch for bubbles. But on the exterior of a habitat in the lunar vacuum, that option does not exist. You are hunting for escaping gas from connections you cannot see directly, in a structure that cannot be fully taken offline and tested. And so, the exterior has another problem. Because there is no atmosphere to slow anything down, tiny bits of rock and metal slam into the surface at tens of kilometers per second. That is 10 times or more faster than a rifle bullet. Most micrometeoroids are the size of a grain of sand or smaller. A good wall stops them. A few meters of regolith stops them reliably, which is another reason to bury the structure. But every impact that does reach an exposed surface chips it, pits it, or stresses it. Over years, millions of tiny impacts create microcraters on every exposed surface. Each crater is a stress concentrator, a place where a future crack can start. And occasionally, a larger piece comes along that threatens something more serious. There are two strategies against this. The first is burial. The deep regolith cover absorbs impacts before they reach the shell. But burial was already in conflict with heat rejection, the problem addressed in the last challenge. Because regolith insulates. It traps the waste heat that needs to escape through emitter panels. That conflict does not go away just because micrometeoroids are also a concern. The second strategy is a multi-layer exterior skin design. Here, the outermost layers absorb an impact, intermediate layers stop any puncture, and the innermost layer holds the pressure while alerting the crew that a section has been compromised. Experimental materials go even further. Layers that melt and reseal around a small puncture, phones that expand into a forming crack. Self-healing structures are a real area of research with some promising lab results. But deploying them at full base scale, in hard vacuum, under constant pressure, with hundreds of degrees of swing and years of abrasive dust grinding, is mostly unexplored territory, and so no exterior shell reduces the risk to zero. A large enough impact can still cause a rapid depressurization in a primary module. When that happens, hatches close, masks go on, the crew stabilizes pressure and finds the breach, and then someone has to go outside and repair it. This is where the spacesuit limit comes in. All exterior repairs on the moon happen in a spacesuit. No exceptions. A suit weighs over 100 kilograms on Earth. It feels like 16 to 18 on the moon, but the mass and inertia are still there. The pressurized gloves that protect the hands also fight every finger movement. Fine work, replacing a small gasket, tightening an awkward bolt, tracing a hairline crack along a curved surface, is far harder and slower than doing the same job with bare hands. A job that takes an hour on Earth might take a full workday in a suit, if it can be done in a single outing at all. And every suited outing burns through consumables at a fixed rate. Oxygen, carbon dioxide scrubber capacity, the cooling water that runs through the suit's thermal system, the battery charge that powers it all. When those consumables approach their limits, the repair is over. Finished or not, the window for each spacewalk is fixed. The job must fit inside it. Or the crew plans a second outing, burning another set of consumables and adding another cycle of risk and effort. Or but, now look at what comes back with them. Every suited worker returning from the outside brings the lunar surface, at least in part, inside. The suit is covered in it, a fine grey powder that clings to the fabric, the joints, the boot soles, the gloves. It does not brush off easily. It does not fall cleanly to the floor like Earth dirt. It sticks. Because lunar dust is not ordinary soil, lunar soil has a name, regolith. It is rock that has been crushed by billions of years of micrometeoroid impacts, ground down particle by particle over geologic time, with no air and no water to soften what the grinding produced. On Earth, minerals that break apart also get tumbled. Rivers carry pieces over rocks. Wind moves grains against each other. Over time, the edges get rounded. The particles become smooth. But lunar regolith has had none of that. Every grain keeps the edge it was born with. Under a microscope, lunar dust looks like broken glass. The Apollo crews noticed it immediately. The dust clung to their suits and tools with a static charge. When they brought it into the lunar module, it scratched their helmet visors. It jammed the joints of equipment. When it mixed with the cabin air, it had a sharp, acrid smell the astronauts described as burnt gunpowder. This was after only a few days of surface operations. A permanent base would face this environment not for days, but for years. With crew constantly moving in and out, equipment running continuously, and operations becoming more intensive over time. This is where the scale of the problem emerges. Lunar dust particles are typically tens of micrometers across, the size of fine smoke particles on Earth, but with edges smoke does not have. In an enclosed environment, particles this size reach the deepest parts of the lungs. The large sand grains you might inhale at a beach stay in the nose and upper airways and are cleared relatively quickly. But fine, angular particles are not. They bypass the body's upper defences and reach the tiny air sacs deep in the lungs where gas exchange happens, where oxygen passes into the bloodstream and carbon dioxide comes out. There they settle, they irritate, they damage tissue. Because on Earth, workers exposed for years to fine silica dust from mining or stone cutting can develop silicosis. The lung tissue scars, breathing becomes impaired, the risk of infection increases. The condition is chronic and progressive. Lunar dust is not the same as industrial silica, but it raises the same fears and possibly more. Some researchers think that regolith grains that have sat in vacuum and under radiation for thousands of years carry chemically active surfaces that may react with tissue more aggressively than ordinary mineral dust. The data is incomplete, but the direction of concern is clear. A base crew would live surrounded by this material. People will go outside, work, and come back. The suits will carry the dust into the airlock. The airlock is where the contamination is supposed to stop. And stopping it completely is an engineering problem no simple door can solve. And so an airlock cannot just be a sealed door, not for years of operations. A real lunar airlock must function more like an industrial clean room. One approach keeps the outer layer of the suit permanently outside, with the crew entering and exiting from a clean inner side, so the contaminated exterior never comes inside. Others use vacuum systems, brushes, gas jets, or vibration to clean the dust off before the inner door opens. Inside, multi-stage filtration captures fine particles, but the filters clog and need to be replaced. And dust levels throughout the habitat would need constant monitoring because contamination always accumulates in ways that are not visible. But the lungs are only part of the problem. The machines face the same one. Consider what tens of micrometer sharp-edged particles do when they get into a bearing, a hinge, or a seal. They act like microscopic sandpaper. They wear away coatings, they cut into lubricants, they open up tiny leak paths through seals. Equipment that could run reliably for years in a clean environment wears out significantly faster when abrasive particles get into every moving interface. Filters in fans and pumps fill up faster. The pumps working against the increased resistance draw more power and wear out faster. Seals that should last for years begin to show degradation in months. And then the dust gets to the power systems. Solar panels on the moon have a real advantage over Earth. No clouds, no atmosphere, no air to reduce the light. The sunlight comes in clean and direct for the 14-day day. But dust settles on every horizontal surface, and solar panels are exactly that. A thin coating reduces the light reaching the cells, and even a few % loss is significant in a system that is at its design limits. This is not theoretical. On Mars, dust on the panels has reduced output enough to end rover missions. On Mars, there are global storms to drive this. On the Moon, there are no global storms, but there is something else. Every surface operation creates local dust clouds. Rovers driving kick it up. Rockets landing and taking off blast it. Construction work disturbs it. In a vacuum, the particles follow ballistic paths instead of drifting in the air, and some become electrically charged by friction or sunlight, causing them to stick to whatever they land on, or even levitate briefly above surfaces. There is no wind to blow the dust away, and no rain to clean the surfaces. What settles, stays. The radiators face the same problem. Radiators work by radiating heat as infrared radiation to the cold sky, and how efficiently they do that depends on the properties of their surface. A thin coating of dust changes those properties. It acts like a thermal blanket, reducing the rate at which heat can escape. A less efficient radiator means the cooling system has to work harder, or operate at higher temperatures, or be built physically larger. Because higher operating temperatures shorten the life of electronics, a larger radiator requires more mass. Every path leads back to the constraints already pressuring the base from other directions. And then there is the question of what happens when the base begins to grow. The longer-term vision for a lunar base involves using local resources, mining regolith for raw materials, extracting the oxygen locked in its minerals, processing metals, printing structural components. Each of these operations intensifies the dust problem. Excavators scoop and dump regolith. Conveyors move it. Crushers break it down further. Reactors heat it to high temperatures to release oxygen. Every step in this chain produces more fine particles, creates more clouds, injects more contamination into the environment around the base. In vacuum, the mechanisms that manage dust on Earth do not apply. Earth's air carries dust in predictable patterns that ventilation can handle. But, on the Moon, particles follow ballistic paths with no drag to slow them, and electrical charging makes them stick to everything they touch. The motors and joints on mining machines are directly exposed. Lubricants for vacuum have to be carefully selected, because standard ones would evaporate or stiffen, and even the best vacuum-rated lubricants face abrasion from grains that are unusually sharp by terrestrial standards. On Earth, heavy mining and construction equipment already requires intensive maintenance. Sand chews up seals and bearings, filters and cutting heads wear out. The industry has built entire support systems around this: workshops, spare parts inventories, specialist technicians, backup machines. But a small crew on a lunar operation has a limited supply of spare parts that came at enormous cost, and a supply run that takes months to arrive. Because the grains are sharper than on Earth. There is no free cleaning provided by rain and wind, and the repair resources are a tiny fraction of what an equivalent Earth operation would need. The dust problem is external. It attacks surfaces, clogs filters, grinds mechanisms. You can see it settle. You can measure it on a panel or in a bearing. In principle, you can build a wall between it and the inside of the base and fight the battle at that boundary. But the next problem has no boundary to fight at. It is already inside. It is the crew. And now comes the real miracle. Because the Moon's gravity is 1.62 meters per second squared. Earth's is 9.81. The ratio roughly 1/6 seems manageable. The person who weighs about 90 kilograms on Earth weighs about 15 kilograms on the Moon. Moving heavy things becomes easy. Physical labor feels lighter. The environment appears forgiving in a way that radiation, dust, and vacuum are not. But this is where things get strange. Because the human body was not built to feel light. It was built for the full weight of Earth. And a gravitational environment that removes 5/6 of that weight does not just make life easier, it can quietly and permanently dismantle the body that depends on it. We have real data on zero gravity. Astronauts lose muscle mass and bone density. Their hearts change shape and workload. Fluids shift toward the head because gravity no longer pulls them down. Faces become puffy, legs become thinner, headaches begin, and pressure on the eyes has been linked to measurable changes in vision. These are not subtle effects. Astronauts exercise for hours every day to slow the damage, and still need months of rehabilitation when they return to Earth. But now consider what the lunar surface actually offers. Not zero gravity, not Earth gravity, something in between. Something that has never been studied in humans for years, not months, years. And that is the gap. Because the ISS data tells us what happens at 0G. Earth tells us what happens at 1G. The Moon sits at 0.16G, and we have no long-term human data for that point on the scale. And so, sending a crew to a permanent lunar base is not entering a well-mapped regime. It is entering a blank space on the map and starting to generate data with the crew's own bodies. Data that cannot be taken back. Let's start with the bones. On the ISS, without aggressive daily countermeasures, astronauts can lose 1 to 2% of their bone mineral density per month. And it is not uniform. It hits the weight-bearing bones the most: the spine, the hips, the legs. Some of this loss is recoverable, some is not. Even if the density returns after long rehabilitation on Earth, the internal architecture can change. Because healthy bone looks like dense support beams, bone that has lost mineral looks more like a hollow lattice. Even if the mass comes back, the strength does not fully return, and so the critical question is whether 1/6 gravity provides enough mechanical loading to prevent bone loss from starting. The skeleton responds to how much force it carries. If it gets strong enough signals, it maintains its density. If they are too weak, the body reabsorbs the mineral as surplus. It is genuinely unknown if 0.16 grams crosses that threshold. If it does not, then treadmills, harnesses, and resistance machines might slow the loss, but not stop it. The crew could spend years losing bone mineral, more slowly than in microgravity, but still losing it, with no way to recover as long as they remain on the surface. A population with progressively thinning bones after 5 years, after 10 years, is a population where a stumble or a fall that would mean nothing on Earth means a fracture on the Moon. Older adults are especially vulnerable. The trap is that once you have a group with weakened skeletons, you cannot just fly them home to rebuild. Much of the damage may be permanent, and flying them home has its own consequences, which are coming in a moment. The bones are just the most visible part. Fluids shift in microgravity because gravity does not pull them down. In 1/6 g, the effect is likely reduced, but likely is not a data point. It is unknown if it's 10% of the microgravity level or 70%. What we do know is that chronic fluid pressure towards the head, even if reduced, could affect vision, raise intracranial pressure, change the environment the brain sits in when sustained for years. In microgravity, these effects are serious enough that agencies are still studying them and have not solved the countermeasures. The moon does not reduce them to zero, it moves them to an unknown point. The cardiovascular system adds another layer. The heart and vessels are tuned to 1G, regulating blood pressure through the constant postural changes of life on Earth. In low gravity, those adjustments are smaller. Over time, the system may decondition to the reduced demand, and the heart muscle itself may weaken if it is no longer pumping against full gravity. Heart shape changes with years of microgravity exposure, and the cardiac risk effects, arrhythmia, heart failure, are still being studied. The brain, in a different pressure and fluid environment, might face changes that only become visible in the later years of a mission. But even all of this, bones, fluids, the heart, is in a sense manageable in that it involves adults who chose to go, understood the risks, and could in principle return to Earth before the damage becomes irreversible. The deepest unknown is not about the crew that arrives. It is about the children that might be born there. Because think about what development actually requires. The bones, muscles, and organs do not just follow a genetic blueprint. They respond to the mechanical environment they grow in. A baby on Earth spends months learning to hold its head up, then to sit, then to stand, then to walk. Each of those stages is a response to the 1G pulling the body down, and the muscles and skeleton adapting to resist that pull. The heart grows by pumping against the full weight of the blood. The inner ear, the balance system, tunes itself to a world where down is a pull of exactly 1G. But in 1/6 G, every one of those signals is different. A baby could sit up with almost no muscular effort because there is so little to resist. The bones receive weaker signals about the load they need to carry. The muscles might develop different fiber ratios. The inner ear might adapt to a world where down is gentle, falling feels slow, standing has almost no cost. By the time that child is a teenager, they may be fundamentally adapted to lunar gravity, not because something went wrong, because the body did exactly what bodies do. It adapted to the environment it actually lived in. Then ask the hard question: could they ever safely visit Earth? Going from 0.16 G to 1G is a roughly 6-fold increase in the gravitational stress on bones, joints, heart, and circulation. A skeleton calibrated for 1/6 G may not be strong enough to carry a body in full gravity. The heart may not be prepared for the extra pumping demand. The spine might compress in ways it was never built to resist. For a person raised on the moon, Earth may not be physiologically accessible. Not hard to visit, not uncomfortable, inaccessible. In the same way that deep water is inaccessible to a body without the equipment to survive it. A moon-born generation that cannot return to Earth is no longer a research outpost. It is a branch of humanity, separated not by distance, but by biology, permanently tuned to a different gravity, permanently locked into the world their bodies were built for, permanently separated from the planet their species emerged on. Even before that generation exists, the adults who go can reach a point of no return. Bone loss and cardiovascular deconditioning over 5 years, 10 years, could mean that a return to Earth requires not weeks, but years of rehabilitation. Some may never fully regain the ability to live in 1G. A mission assignment that began as temporary could become permanent, not by choice, but by biology. And the ethics of sending people under those conditions is not a simple calculation. The biology of the crew is only one piece of what this small team now has to manage. Because The base still needs power. It still needs materials. It still needs water. And the question of where the water comes from is one that on its own branches into almost everything else. Behind every breath you take, there is a machine that just made it. On Earth, this fact is never noticed. The atmosphere handles the chemistry. The oceans, the forests, and billions of years of biology have built a life support system so vast and redundant that one human's exhalation barely moves the needle. There is always more air. There is always somewhere for waste to go. The planet itself is the infrastructure, and it runs without a maintenance crew. But on the Moon, none of that background exists. Every single molecule of breathable air inside a habitat is there because a machine recently made it. And every molecule of carbon dioxide from every breath must be captured and processed by another machine. If one of them stops, the atmosphere drifts toward conditions that are first uncomfortable, then dangerous, then fatal. In a small sealed space with non-working removal, CO2 rises quickly. First headaches, then confusion, then unconsciousness, then death. The timeline from normal to fatal is measured in hours, not days, and CO2 is only part of what the air system handles. Humans release water vapor. They shed skin particles. Plastics, electronics, and adhesives off gas. Trace chemicals that on Earth would simply dissipate into the outer atmosphere. Inside a sealed habitat, they build up, with no wind to dilute them and no window to open. And so, CO2 scrubbers, oxygen generators, and trace contaminant filters must all run continuously, every hour of every day, for the entire mission. Not for weeks, for years. The International Space Station already does this. It has chemical scrubbers and oxygen generating systems, and the crew breathes recycled air. And so, it might seem like a solved problem, something we already know how to do. But the ISS is not a closed loop. It leans heavily on Earth. When a scrubber cartridge is spent, a cargo vehicle brings new ones. When a pump fails, a spare arrives in weeks. The ISS shows the technology works when the supply chain is still robust and fast. But a lunar base cannot rely on that. Every filter, every canister, every spare pump is a mass that had to survive the rocket equation. The systems must be far more closed loop, far more reusable, and far more repairable by whoever is there, with whatever is on the shelf. This is not harder by a small margin, it is harder by a different standard. Water makes the constraint even tighter. A human needs a few litres of drinking water a day. Add washing and cooking, and the figure rises to tens of litres per person per day. The total for a small crew over years is enormous, and sending it all from Earth is not viable beyond a short demonstration. Almost every drop must be captured and reused. Processing urine back to drinking water, condensing moisture from the air, treating and recycling grey water. The ISS already recycles about 90% of its water, a real achievement. But those systems are not light, simple, or maintenance-free. They need filter changes, pump servicing, and component replacements. And on the ISS, when something fails, ground control sends a spare. But on the Moon, if the main water recycler fails and there is no spare on site, the crew starts counting days, literally counting what is left in the tanks. And no fallback plan comes without its own complexity. Processing ice from permanently shadowed craters requires power, machinery, and its own maintenance chain. Stored tanks that form the emergency buffer are limited, and they are limited by the same mass penalty that governs everything. There are no neighbours, no well to go to, just what the machines are producing right now with what they have on hand. Food hits the same wall. Short missions can carry freeze-dried provisions. A crew of 3 for 6 months is a manageable supply problem. But a base operating for years with more people turns this into a constant, expensive logistics chain that gets heavier with every additional crew member and every additional year of operation. At some point, the choice becomes binary. You either keep the base permanently small and rotational, or you grow food locally. Growing food locally means large hydroponic or aeroponic farms, or something more ambitious. Full bioregenerative life support, where plants, algae tanks, and possibly insect farming provide a significant fraction of the food supply, while also recycling CO2 back to oxygen and processing biological waste into nutrients. These systems can do real work, but they are not machines in the same way a pump or a filter is. They are ecosystems, and ecosystems crash. A fungus spreads through a crop. A nutrient imbalance stresses the plants before anyone notices. A lighting failure for 4 hours at a critical growth stage. A temperature spike kills a batch. On Earth, a failed greenhouse can be recovered. Seeds, backup soil, food from somewhere else while you rebuild. But, on the Moon, a major crop failure directly hits food security. And the only buffer is stored provisions, limited by mass and shelf life. There is no somewhere else. And so, tuning a bioregenerative system is a slow, skilled job that requires deep knowledge of plant biology and chemistry in a low-gravity, artificial light, unusual radiation background atmosphere that could affect growth in ways that have never been studied at scale. The rule that runs through air, water, and food is the same. There is no safe downtime. On Earth, a power cut that takes out the HVAC is an inconvenience. It is dangerous mainly for the vulnerable, rarely fatal for a healthy adult. But, on the Moon, losing environmental control for just a few hours can push conditions beyond lethal thresholds. CO2 scrubbing stops and levels rise. Fans stop and stale air pockets form. Humidity control fails and condensation forms inside electronics. Cooling fails and the interior heats up. Heating fails during the night and temperatures drift toward freezing, threatening pipes, tanks, and people. The obvious answer is redundancy. Multiple scrubbers, pumps, fans, backup power, emergency oxygen. And redundancy is correct, but every backup is more hardware that was launched via the rocket equation, more plumbing, wiring, and sensors that are maintained by the same small crew. But now stop and think, because these machines have a hidden failure mode too. If 2 scrubbers share a single software controller, a single bug takes out both. If 2 pumps come from the same flawed manufacturing batch, they can fail together under the same conditions. And so, redundancy protects against independent failures, not common cause ones. And a base built with limited suppliers and few part variations is especially vulnerable to them. Because there is no open window, no stepping outside for fresh air. Everything the crew breathes, drinks, and eats must be constantly produced, reclaimed, and maintained by systems that cannot just afford to work most of the time, but must be continuously reliable, repairable by a small team under pressure for decades. This is a standard we struggle to meet even in Earth's most safety-critical infrastructures, hospitals, submarines, power plants, when they have large, dedicated teams and full supply chains behind them. But, on the Moon, it is demanded of an entire artificial environment, run by a handful of people who are also doing everything else. And all of this runs on power, delivered without interruption, through the full lunar cycle. Power is not a background condition. It is the thing every other system quietly assumes. The scrubbers run on it. The water cycles run on it. The grow lights, the pumps, the heaters, the communications array, the medical equipment, all run on it. And so our base that demands uninterrupted power through the full lunar cycle is not rhetorical. It is the load that underlies everything else. So where does that power actually come from? A modest science outpost draws tens of kilowatts just for life support. Add crop lighting, an excavator, a regolith processing furnace, computers, a medical centre, and you reach hundreds of kilowatts. Scale to a real outpost with industrial activity, and you reach the megawatt level of demand. This is equivalent to the power drawn by a small town on a quiet afternoon. On Earth, this comes from a grid with backup sources, transmission that crosses continents, and utilities with fleets of repair crews and warehouses. But on the Moon, it comes from hardware the crew has shipped, set up on rough terrain, and now keeps running with their own hands. The first instinct is solar. It is a reasonable instinct. The lunar surface receives roughly 1,300 to 1,400 watts of sunlight per square meter, unfiltered by an atmosphere, with no clouds to interrupt. Panels work efficiently in these conditions. The sunlight is clean, direct, and reliable. For about half the lunar month, solar is indeed excellent. But that half of the lunar month is followed by the other half. The sun sets, and it stays down for about 350 hours. Not for a night, for 2 full weeks of continuous darkness. The solar output during this time drops to essentially zero. The math to get through this quickly becomes uncomfortable. A base drawing an average of 500 kilowatts over 350 hours of darkness needs stored energy in the range of 175 megawatt hours, not 175 kilowatt hours, the kind of figure that defines a serious home battery. A full 175 megawatt hours. The battery farms or fuel cell systems that could hold this energy would weigh tens, potentially hundreds of tons, plus the inverters, control gear, and thermal management hardware just to keep those systems running safely. And this is just the night storage problem. The solar array has its own challenges. Panels degrade under lunar radiation as particles damage the cells. Micrometeoroids pit the surfaces. Dust from rovers, landers, and construction settles on the panels and cuts the output. And cleaning is a trap. Brushing risks scratching the glass. Blowing gas consumes a resource. Automated systems are more machines that can fail, because the array has to provide the base load during the day and charge those massive storage banks. The solar farm grows to cover multiple football fields of rough terrain. It is connected over long cable runs that have to survive dust, radiation, and the full thermal cycle. Every panel means more connectors. Every cable run can be cut, shorted, or degraded, and repairing a break in the field may require a spacewalk. The nuclear option solves the night problem cleanly. A compact reactor provides continuous output, day and night, completely ignoring the lunar cycle. It reduces the storage requirement to something far more manageable. The logic is compelling. But a reactor on the moon is its own bomb of complexity. First, it has to get there. Launching fissile material means convincing regulators and the public that the non-zero chance of a launch failure is acceptable. Because rockets fail rarely, but rarely is not never. And a vehicle breaking up carries different consequences when its payload is nuclear fuel. Second, the crew has to assemble the reactor, shielding, and cooling on the surface, with no ready infrastructure. A plant on Earth plugs into an existing grid with a full regulatory framework, a professional workforce, and a spare parts supply chain. But on the moon, the grid is the cables the crew lays. The spares are what fit on the last cargo manifest, and the regulations are still being written. Third, the reactor has to run for years, shedding heat through radiators that are exposed to the same dust and micrometeoroids that degrade every other surface. At the end of its life, there is no storage pool, no licensed repository. Just a hot, radioactive machine on the surface that must not contaminate the ice. The water supply depends on it. It is not a solved problem, it is a permanent one. Thing else. So where does that power actually come from? A modest science outpost draws tens of kilowatts just for life support. Add crop lighting, an excavator, a regolith processing furnace, computers, a medical centre, and you reach hundreds of kilowatts. Scale to a real outpost with industrial activity, and you reach the megawatt level of demand. This is equivalent to the power drawn by a small town on a quiet afternoon. On Earth, this comes from a grid with backup sources, transmission that crosses continents, and utilities with fleets of repair crews and warehouses. But on the Moon, it comes from hardware the crew has shipped, set up on rough terrain, and now keeps running with their own hands. The first instinct is solar. It is a reasonable instinct. The lunar surface receives roughly 1,300 to 1,400 watts of sunlight per square meter, unfiltered by an atmosphere, with no clouds to interrupt. Panels work efficiently in these conditions. The sunlight is clean, direct, and reliable. For about half the lunar month, solar is indeed excellent. But that half of the lunar month is followed by the other half. The sun sets, and it stays down for about 350 hours. Not for a night, for 2 full weeks of continuous darkness. The solar output during this time drops to essentially zero. The math to get through this quickly becomes uncomfortable. A base drawing an average of 500 kilowatts over 350 hours of darkness needs stored energy in the range of 175 megawatt hours, not 175 kilowatt hours, the kind of figure that defines a serious home battery. A full 175 megawatt hours. The battery farms or fuel cell systems that could hold this energy would weigh tens, potentially hundreds of tons, plus the inverters, control gear, and thermal management hardware just to keep those systems running safely. And this is just the night storage problem. The solar array has its own challenges. Panels degrade under lunar radiation as particles damage the cells. Micrometeoroids pit the surfaces. Dust from rovers, landers, and construction settles on the panels and cuts the output. And cleaning is a trap. Brushing risks scratching the glass. Blowing gas consumes a resource. Automated systems are more machines that can fail, because the array has to provide the base load during the day and charge those massive storage banks. The solar farm grows to cover multiple football fields of rough terrain. It is connected over long cable runs that have to survive dust, radiation, and the full thermal cycle. Every panel means more connectors. Every cable run can be cut, shorted, or degraded, and repairing a break in the field may require a spacewalk. The nuclear option solves the night problem cleanly. A compact reactor provides continuous output, day and night, completely ignoring the lunar cycle. It reduces the storage requirement to something far more manageable. The logic is compelling. But a reactor on the moon is its own bomb of complexity. First, it has to get there. Launching fissile material means convincing regulators and the public that the non-zero chance of a launch failure is acceptable. Because rockets fail rarely, but rarely is not never. And a vehicle breaking up carries different consequences when its payload is nuclear fuel. Second, the crew has to assemble the reactor, shielding, and cooling on the surface, with no ready infrastructure. A plant on Earth plugs into an existing grid, with a full regulatory framework, a professional workforce, and a spare parts supply chain. But on the moon, the grid is the cables the crew lays. The spares are what fit on the last cargo manifest, and the regulations are still being written. Third, the reactor has to run for years, shedding heat through radiators that are exposed to the same dust and micrometeoroids that degrade every other surface. At the end of its life, there is no storage pool, no licensed repository. Just a hot, radioactive machine on the surface that must not contaminate the ice. The water supply depends on it. It is not a solved problem, it is a permanent one. The likely architecture is a hybrid, solar for flexibility during the day, nuclear for baseload through the night, large storage to fill the gaps and absorb transients when one source stumbles. On paper, the combination meets the requirements. But, in practice, the small crew is now running a power company where every repair is hard. Surface travel is slow, and the spare parts inventory is exactly what was shipped, and no more. And there is no external grid to fall back on. On Earth, when one plant goes offline, others absorb the load. When a substation fails, dispatchers reroute. When a storm takes down transmission lines, utility crews come in from neighbouring territories in hours. The system has depth. Most of it is invisible under normal conditions. But, on the moon, the grid is the base. There is no adjacent territory, no upstream utility. The full depth of the system is the crew standing in front of it. And now consider what a serious power event looks like. Dust has been building up on the solar panels for weeks, cutting output first by a few percent, then more. At the same time, a blockage develops in a cooling loop on the reactor, and the automated safety system does what it was designed to do. It shuts the reactor down, scramming it to prevent damage. The batteries begin to discharge to cover the combined shortfall. Then, a software bug in the power management system overestimates the remaining battery capacity and continues to discharge for longer than it should. If everything goes right from this point, the crew diagnoses the coolant blockage, clears it, restarts the reactor, and recharges the batteries before any system reaches a critical threshold. That is the good outcome. But if something goes wrong, the situation cascades deeper. A valve needed for the restart does not actuate. An operator misreads a stuck sensor for the real coolant pressure. Module temperatures drift beyond the point where water processing has to be suspended to preserve hardware. The CO2 scrubbers on reduced power approach their limits. And so, within hours, the crew is evacuating outer sections, crowding into a smaller emergency core with better power and shielding. They are breathing from backup tanks. They are managing their own stress while planning a complex repair in a suit under a 14-hour cold soak. Because, on Earth, teams from the outside bring parts and stabilize the system. But, on the Moon, the only technicians are already there. They are the people in the emergency shelter. They are the ones who have to fix it now. Because power connects to air, water, food, heating, and communications all at once. A serious power event does not threaten one system. It threatens all of them simultaneously, through every dependency already documented in the sections above. And so, what the base requires is a power plant on the scale and reliability of a small terrestrial grid built entirely from rocket-delivered equipment run by a crew the size of a small office, maintained without outside assistance over stretches that can last for years. It is not an engineering subsystem. It is a civilization-level demand with one's name on it. And power is still not the deepest layer. Underneath it lies the question of what raw materials the base runs on and where all those tons of processed feedstock come from. Let's assume the power holds, the grid works. The reactors are stable, or the battery farms are charged, or a hybrid of both has survived the lunar night. Then what are the walls made of? Because every serious plan for a lunar base eventually arrives at the same answer. You cannot keep importing the physical structure of the base from Earth. The launch cost alone makes it untenable. Every single pressurized module, a room, a hallway, a storage tank, costs more than almost anything humanity has ever moved. At some point, the base must grow beyond what rockets can carry, and that means building with what is already there. And so, the lunar surface is covered in regolith, tens of meters deep in most places. The raw material is everywhere. Melt it, press it, sinter it into bricks, beams, landing pads and radiation walls. Extract the oxygen locked inside its oxides. Pull out the aluminium and iron. On paper, the logic is clean. But, in practice, it opens an entirely new layer of the problem. Because lunar regolith is not Earth construction material. That distinction sounds small. It is not. Portland cement, the standard binder that holds together almost every concrete structure on Earth, is made from limestone and clay, processed with heat and water. The resulting chemistry is specific and well understood. Earth building codes, construction standards, material safety factors are all built on centuries of working with this material. On the Moon, none of the inputs are waiting in a usable form. No limestone quarry, no clay bed, no accessible liquid water, no Portland cement, and no easy substitute. What the regolith does contain is silicates and oxides of silicon, aluminium, iron, magnesium, calcium, and titanium. The elements are there, but in different ratios and mineral forms from anything engineers know the recipe for. And so making anything structural requires serious energy. Sintering, heating until the grains fuse, means hundreds of degrees Celsius. Melting it completely and casting it means getting over 1,000 degrees. Making glass, pulling out metals, producing ceramics, all happen in similar or higher ranges and require stable power, robust heaters, insulated crucibles, controlled molds, and carefully managed cooling. This is not a side operation. This is a full industrial process. And this is where the logic bends. ISARU, the dream of building locally with local materials, does not eliminate the industrial infrastructure problem. It moves it. Instead of steel mills and cement plants on Earth shipping components, you build some version of those plants on the Moon. They run off the same fragile power grid. They are maintained by the same small crew that is already running life support and thermal control. And they consume a feedstock that is sharp, abrasive, and chemically variable from one site to another. The concept videos show it simply. a robotic arm laying down smooth layers of molten regolith, building up a dome ring by ring, perfectly uniform and sealed. But real regolith is not uniform. The grain sizes range from dust finer than flour to small pebbles. When you heat a batch, some grains melt completely, others only partially, others stay solid. The result is not a homogeneous material, but a mix of fused and unfused particles with voids, weak spots, and stress concentrations locked inside. Then comes the cooling. Different minerals expand and contract by different amounts. And so, as the structure cools and its geometry locks in, these mismatched rates seed micro cracks throughout the material. The cracks might be invisible and not fail immediately, but they grow under repeated thermal cycling. And the Moon delivers that constantly. Every exterior structure faces swings measured in hundreds of degrees every single lunar month. It is not a flaw in the design, but a fundamental feature of the material and the environment. And so, to build reliably with regolith, you need more than a printer. You need quality control of the feedstock before heating, precise heating and cooling profiles, and inspection of the finished parts for hidden flaws. On Earth, this means X-rays, ultrasound, destructive sampling, and safety factors based on decades of watching similar materials succeed and fail. But on the Moon, you start with almost none of that. Because there is no long database of how regolith-derived materials age under the combined vacuum, radiation, micrometeoroid bombardment, and large thermal swings. Every printed arch, sintered block, and cast beam is closer to an experiment than a validated product. You would likely need binders and reinforcements on top of the basic regolith, metals embedded as rebar, woven fibers for tensile strength, polymers imported from Earth to hold layers together. Every addition brings more logistics, mass, more process complexity, more steps where something can go wrong in a facility that has no external technical support and very limited backup capacity. And then the problem scales up again. Building the structures is one challenge. Maintaining the machines that build the structures is another. To truly reduce dependence on Earth, those machines have to support themselves. Because gears wear, bearings fail, shafts break, casings crack, pipes develop leaks. Every mechanical component in the furnace, the printer, the excavator, the conveyor system, has a limited service life. On Earth, you order a spare. But on the Moon, you either make it locally or you wait for the next cargo window. Making it locally means machine tools, foundries to cast raw metal shapes, small metallurgy labs to refine the right alloys for the right applications. It is a second industrial layer that sits on top of the first. When you push it further, the ceiling becomes visible. Truly independent manufacturing eventually requires electronics fabrication, and the computers and sensors that run every other system are not simple mechanical parts. Because semiconductor manufacturing is among the most complex activities civilization has ever created. Ultra-clean rooms where a single particle of dust ruins a component. Dozens of chemical processes requiring purities measured in parts per billion. Lithography that writes patterns smaller than a wavelength of light, and a global supply chain that feeds in hundreds of specialized inputs from dozens of countries. To expect a lunar outpost of a few dozen people to build anything approaching this from local resources is not ambitious. It is closer to asking a remote Antarctic research station to build a full steel mill, an aircraft factory, and a semiconductor fab with a few crates of starter equipment and the nearby ice and rock. Even if the industrial problems are solved, the materials carry unknowns. Regolith glass might darken or become brittle under radiation faster than models predict. Sintered blocks might slowly crack along hidden internal planes over years. Embedded metal reinforcement might corrode in unexpected ways when exposed to the trace chemicals from life support exhaust that recirculate in a closed environment. Structures optimized for 1/6 gravity might behave unexpectedly under internal pressurization or when carrying heavier than planned equipment. On Earth, building codes evolved from observation. Bridges stood or fell. Towers cracked or held. Engineers watched real structures age and updated their models. And the knowledge now embedded in construction standards represents centuries of trial and error, much of it paid for by structures that underperformed. But the Moon has none of that record. Every dome, tunnel, and printed wall is among the first of its kind ever built from these materials in that environment. No one knows with confidence how they will behave in year 5, year 10, or year 20. And so, a miscalculation is not a crack in an unused building. It is a hairline failure propagating across a pressurized habitat roof. A slow weakening in a radiation shield that was expected to last for decades. A structural element that performs perfectly for 10 years and fails in year 11. In an environment where there is no margin for the material behavior to have been wrong over time. ISRU does not solve the problem. It trades one version of the problem for another. Instead of enormous launch costs for finished buildings, the base pays enormous complexity costs for a local industry with no precedent, no safety database, no backup capacity for error, and no recourse when the materials it produces behave differently than expected. And all of it is still tethered to Earth for the high-end components the local industry cannot yet make. The supply chain does not go away, it changes shape, and the base, which gets heavier and more complex with every added section, reaches further and further along that chain with every passing year. Let's start with what in-situ resource utilization truly cannot provide. Regolith provides bulk rock, some structural metals, eventually oxygen if the processing holds. But a working habitat is not made of bulk material. It is thousands of specialized items, each with its own supply story. Pharmaceuticals with specific storage and expiration processes, memory and sensors, specialty alloys for valve seats and pressure seals, pumps, bearings, inspection tools, instruments, cables, circuit boards, adhesives, replacement suits. None of it comes from a regolith furnace. All of it comes from Earth, flown across 384,000 kilometers, landed and carried inside. And here the supply chain reveals its first quiet danger. It is not always the most expensive item that is the most critical. $1 million pump can sit idle for want of a $5 gasket. A critical environmental control unit can go offline because a tiny sensor failed. On Earth, a missing part is a phone call and an overnight delivery. But, on the Moon, if it was not on the last cargo manifest, the crew waits. Not for days, for months. The system runs degraded or not at all, and the base absorbs the strain. Because that wait time is not random. It is set by orbital mechanics. The geometry where launches are cheapest recurs on a schedule the base cannot negotiate, and so, a part urgently needed in March might not realistically fly until a window opens late in the summer. Every cargo manifest is a bargain between urgency, mass limits, cost, and the probability of any given item breaking next. Send too many spares and costs balloon, payload is wasted. Send too few, and a system stays down because a small, unique component broke with nothing to replace it. This is why the launch cadence is not a business detail, not a planning preference, but a life support parameter. A rhythm to which human bodies and aging hardware are tied. People eat every day. Medications expire on a calendar that does not care about orbital windows. Equipment wears out at a rate set by the lunar environment, not by the resupply schedule. When a launch is delayed from June to October, the base does not pause, its clock keeps running. But launches are delayed. Because rockets are not buses on a fixed route. Engines and tanks wear out. Launch pads erode and crack from repeated firings. Weather cancels attempts. A major accident can ground an entire family of rockets, sometimes for a year, while investigators work. A recession cuts funding. A war disrupts component supply chains no planet ever predicted. These are not theoretical risks. They are the normal background noise of complex industrial systems on Earth. The base on the Moon inherits all of it, filtered through a single thread. On Earth, that single thread is not how supply chains work. A container ship that cannot reach its destination triggers a reroute by air, rail, or truck. Insurance absorbs the shock. Multiple suppliers compete for the same contracts. Warehouses hold buffer stock measured in months. When one link fails, others take the load, because the network is designed around the assumption that individual links will fail. Complex societies feel stable because of this depth. The buffer is invisible until it is needed, and then it is there. But in cislunar space, this depth barely exists. If a cargo lander fails in transit, the food and medicine it was carrying are gone. There is no warehouse in lunar orbit holding a reserve. There is no neighbouring colony to borrow from. If an Earth manufacturer stops making a critical component, there may be no second source qualified for space, and qualifying a new one takes years of testing and certification. Switching launch providers is not like booking a different airline. Payload interfaces and safety certifications are specific to each vehicle, and redoing that work takes time the base may not have. Something else was happening. The supply chain does not just affect what the base has, it affects how quickly the base can fix what breaks. A design flaw discovered on Earth follows a rapid cycle. Engineers redesign in days, a prototype is machined and tested, the fix goes into production, and spare parts ship in weeks. But, on the Moon, that same cycle stretches until it is almost unrecognizable. The redesign and testing now carry extra certification, because a failure on the Moon cannot be addressed quickly. Production is scheduled, the parts are packed into cargo modules and placed on a manifest, then wait for a launch window. After launch comes transit, orbital insertion, landing, and unloading. Only then can the crew install them. The cycle is not days or weeks, but months, sometimes longer. All that time, the base keeps running. It operates the flawed component more carefully, with extra monitoring and increased risk. Or it shuts down the affected system and puts more load on the backups, stressing them as well. Every hardware improvement, every bug fix, every upgrade moves at the speed of orbital mechanics and launch schedules. Not the speed of overnight cargo, not a software patch, but the speed of rockets and orbits. This slowness reaches deeper than repair timelines. It shapes how the base behaves toward change. In a harsh environment, you want rapid iteration, to try something and adjust when reality is different from the simulation. But every iteration on the Moon is long and expensive, and backing it out is slow and risky. And so, the crew becomes hesitant to experiment with critical systems, because being wrong costs months of degraded operation. A conservative engineering culture develops, prudent and wise in some ways, but ill-suited to respond quickly when the environment reveals something no model predicted, which it does, constantly. And the hardware that arrived has been quietly aging since the day it was installed, sitting in radiation, dust, and thermal cycling. It will fail. The question is not if, the question is when, and whether the base has enough spares, enough tools, and enough skilled people to patch it back together faster than the environment is tearing it apart. That hardware, aging quietly, is not a background detail. It is the central problem. Every system on the base has a rated service life. Every component came with a datasheet that listed its expected failure intervals and maintenance schedules. On paper, a lunar base is a set of systems with known lifespans and predictable needs. But, in reality, it is hardware being worn down by an environment harsher than any lab that wrote its specifications ever predicted. Space ages materials in ways Earth never does. Electronics are constantly exposed to radiation. High-energy particles flip memory bits, damage transistors, and slowly degrade the material. A control card rated for 10 years of service, tested in a climate-controlled building, will not live for 10 years on the Moon. Exposed to more radiation, violent thermal cycling, and the shock of launch and landing, that same card might quietly become a 3 to 5 year part, or less. The rating on the datasheet does not change, the card does. And electronics are just one aging mode. Lubricants outgas in a vacuum. The oils and greases that keep bearings running evaporate, degrade, or migrate away from the surfaces they protect. Polymers become brittle under radiation and temperature swings. Seals harden. Insulation cracks. Metals fatigue from thousands of expansion-contraction cycles. Solder joints flex until they crack. Connectors loosen. Cables stiffen and break from within. Each is slow. Each is invisible, until it is not. In this video, we saw how hard it is to settle on the moon. But I didn't tell you the real danger. It's not just space, but the universe itself that is trying to destroy us. Dark energy, an invisible force born from the vacuum of space itself, tearing galaxies apart from one another. On our next journey, we will unlock the secret of this force that is ripping the universe apart. Are you ready for this cosmic apocalypse?